stretch out the waves in the direction it is moving away from, and these changes can be measured and considered. So this is what's known as the Doppler effect. And actually, you probably recognize it as you hear the falling note of a car or train horn as it approaches, passes, and goes away from you. So that change in pitch is the Doppler effect. Now, at a bigger level, we can work out that for an object that's moving with a speed much less than that of light, it can be shown that this change in frequency is given by the change in frequency divided by the original frequency is equal to the ratio of the speed of the object divided by the speed of light, assuming the velocity of the object is much less than the speed of light itself. Now, that same equation, we can review and convert it to think about it with terms of wavelength. So the change of wavelength is equal, divided by the original wavelength, is equal to minus the speed of the object divided by the speed of light. So this is what happens when we're thinking about light waves as it happens. Now note the negative number there. There's things to think about with positive and negative values. Objects moving towards the observer have a positive speed, so moving away from the observer has a negative speed. So if the object is moving away, the frequency is lower, so therefore the change in frequency is negative, and therefore the change in wavelength will be longer. If the object is going towards the observer, the frequency is higher, so the change in frequency will be positive, and the wavelength will therefore be shorter. So that's the key thing about the values there. Now, when we're talking about light, this is known as something called redshift, because the minus sign tells us the star is receding away from us, and the longer wavelength is called redshift because it's normally been shifted towards the red end of the spectrum. So if we look at two emission spectra, what we can see here is the distinctive lines which we can capture have been shifted along. Okay? And so the distinctive lines we can see a red line there, and we can see a purple line there, and we can see that it has shifted along. So we see the pattern is the same, but the colors are different. And that tells us something about what's happened to the star, and it means we can look at if it has been redshifted, and from there work out how fast it's been moving. So let me give an example. The wavelength of pale blue line in the hydrogen spectrum is 486.27 nanometers. It was measured in the lab. Now, the same spectral lines looked at in a star, the wavelength is now 486.94 nanometers. So what is the speed of recession? So in this case, we'll use our formula to find out the change in wavelength for 0.67 nanometers, or 0.67 times 10 to the minus 9 meters. If we substitute this value in, and we know that the speed of light is 3 times 10 to the 8 meters, it means that my recessional speed is 4.1 times 10 to the 5 meters per second. I can work out the speed of the star. There's some other applications for the Doppler effect, and that would be rotational periods of planets we can work out, the rotational period of a star, and also, interestingly, orbital period of binary stars. So let's look at the orbital period of a planet to start with. If Venus has a diameter of 12,200 kilometers and a rotational period of 243 days, that means I can think about its angular velocity and its linear speed of rotation at the equator. To do that, the angular velocity is going to be 2 pi divided by the period. So that's 2 pi divided by 243 times 864 seconds, which comes out as 2.99 times 10 to the minus 7 radians per second. Now, if I know that, then, and I also know what the radius is, so diameter divided by 2, it means I can work out the linear speed at the equator, and that comes out at 1.81 meters per second. Now, if the radio waves of wavelength 1 meter are used to determine the speed of rotation, what is the expected shift in wavelength reflected at the opposite edges of the equator? So what's going to happen is that the wavelength which reflects back is going to be different at either side of the edges of the equator. Okay, so I need to think about this a little bit. Here, if I use the change in wavelength is going to be divided by the wavelength equals minus v divided by c. Now, what I can say is that my change in wavelength is going to be minus 1.81 meters per second. So that's going to be the velocity times 1 meter, which is the wavelength of the radio waves being fired at them, divided by 3 times 10 to the 8 meters per second, which is the speed of light. And that tells me that the change in wavelength is going to be 6.03 times 10 to the minus 9 meters. I can use this to clarify and measure the orbital period by using this original number. Exactly the same process is going to take place to work out the rotation of a star. What we'll see is that on one side of it, it will be slightly shifted to the red, and one side it will be slightly shifted to the blue. And therefore I can work out the relative rotation or speed of a star through this process. Now, binary systems, in fact, 60% of all stars are actually pairs, making our sun as a single star kind of a minority. Now, binary stars are another interesting feature because we can use this idea of the Doppler shift to work out lots of information about these stars. If the stars are of equal mass, what will happen is they'll rotate around like this. The center of mass will be exactly in the middle, and they'll be circling that central point. But not all binary stars are like this. Some binary stars are so far away, or their rotational orbit is so small, we can't distinguish between them. And in that case, we just have to rely upon the information which is given off from the star and actually looking at the Doppler shift which takes place. We also see sometimes these weird situations where if one star is very much bigger than the other star, then what we find is that they'd rotate around a little bit like this. The more massive star means that the center of mass is still in the central location, but its rotation is in the inside of a smaller star, which is rotating around. So these are some types of binary systems. Now, one type of binary system is an eclipsing binary star system. In this case, what we see is the smaller star will eclipse the larger star for a period of time. Now, they're still quite close together. So when we see them normally, what happens is we have a combined intensity. Number 2 sees the eclipsing effect. The smaller star stops the light coming from the brighter star, so the intensity drops. Then the small star in part 3. We can see both stars. We have the normal intensity. And then the smaller star goes behind the brighter star, and therefore there'll be a slight drop in the intensity before it rotates around again to number 5 and through to number 6. And this process goes on and on and on. Now, this means that we can work out and recognize if it's a binary star system because we'll see an intensity pattern like this. Now, spectroscopic binary stars are stars which we can only tell are binary because the Doppler shift tells us. So, if we look at a single line, we know is yellow in the lab. The line for star A is blue shifted, which means it has a shorter wavelength, so it's approaching us. And the line for B is red shifted, which means the star is going away from us. Now notice that the stars have moved in their orbit, and the blue shift and the red shift are a little less this time. Now, in this situation, neither star is moving towards us or away from us, so there's no shift at all. Now, here's an example. A star is moving away from the Earth at 5,000 kilometers per second. A certain wavelength has been detected in its spectrum, which corresponds to a line of wavelength 350 nanometers as measured in the laboratory. What is the wavelength of this line? So think about it. I'm going to put up questions, so pause now, do your calculations. Now here, your new wavelength should have been 355.83 nanometers. The star is receding, so we add the differences to the wavelength.